Modern artificial intelligence systems are now reliably succeeding at some of the most difficult, search-oriented optimization tasks in computer science. We see this across entirely different domains. Neural networks coupled with tree search achieved superhuman play in the game of Go, and recent agentic systems have demonstrated strong performance in solving Olympiad-level formal geometry. These achievements share a specific mathematical profile. They belong to problem classes where checking a proposed answer is computationally easy, but searching for that exact answer among trillions of possibilities is classically hard. This creates a theoretical paradox. If artificial intelligence can consistently solve these problems, we have to ask if difficult search has become uniformly tractable. A positive answer would effectively prove that P equals NP, collapsing one of the central questions in mathematics. Alternatively, if we assume P does not equal NP, we face an inverse dilemma. We would have to conclude that intelligence operates completely outside the formal bounds of theoretical computer science. AI's success exploits a specific, rigorous mathematical phenomenon, polynomial time reachability. It does not break classical complexity limits, nor does it require a mystical explanation. To understand how this works, we must separate two concepts that are often conflated. There is a vast difference between a solution mathematically existing and a computer system actually reaching that solution under strictly bounded time. This map visualizes computational limits. The outer boundary separates computable tasks from undecidable problems. The inner boundary isolates tasks solvable in bounded polynomial time. Between strict polynomial time and the outer computable boundary, like graded strata, NP and PH, representing progressively richer forms of access, artificial intelligence operates inside this transitional space. It pushes outward from the core, systematically expanding the frontier of what a system can reach in polynomial time. In complexity theory, deterministic polynomial time, the core we just looked at, serves as the accepted theoretical baseline. It defines tractable, bounded, direct decision-making. This chart illustrates the first major widening of that baseline, the class NP. In this framework, NP functions as a strict structural mechanism for polynomial time certificate verification. Within NP, a bounded witness, a candidate solution, does not have to be generated by direct deterministic search. It only needs to be checked efficiently once it is proposed to the verifier. Boolean satisfiability is the canonical example. Checking if a massive string of logical variables evaluates to true takes almost zero time. Finding the exact arrangement of variables that produces that true result is notoriously difficult. By separating the proposal from the check, NP records the transition from direct computation to recognized access. This provides the structural foundation for AI systems that generate and evaluate candidate solutions. The polynomial hierarchy captures further widenings by adding structured adversarial interaction to the verifications. This diagram maps out Theorem 2. Moving up the polynomial hierarchy is mathematically defined by adding bounded alternating quantifier blocks. Specifically, it uses existential variables, denoted by E, and universal variables, denoted by A. This mathematical notation defines a formal bounded verification protocol of proposal, challenge, and reply.
Consider a depth 3 protocol. An AI existentially proposes a solution. An internal universal critic poses a bounded challenge, scanning for flaws. Finally, the AI repairs the identified flaw, before a final polynomial time check determines success. This alternating mathematical structure perfectly mirrors modern AI architecture. When engineers build agentic loops that ask an AI to draft, critique, and revise an answer, they are executing this exact formal protocol. Each step up the hierarchy internalizes what was previously external, blind search. It absorbs that search into a governed verification game executed within polynomial time limits. If we can indefinitely stack these verification layers to mimic human reasoning, we have to establish the absolute mathematical ceiling. This visual represents the paper's specific limiting process. It defines intelligence as the union of all finite depth verification games, an ever-expanding but strictly finite ladder. Contrast this finite limit with alternating polynomial time. In that regime, the number of interaction layers is not fixed. It is allowed to scale infinitely with the size of the input data. Theorem 4 proves that this unbounded alternating regime is mathematically equivalent to p-space, a radically more powerful complexity class.
By defining the limit at the finite union, we lock the target phenomenon strictly below that upper bound. Modern machine intelligence does not require infinite p-space-level oracles. It operates entirely within the rigorous, finite-depth stage descent of the polynomial hierarchy. In practice, artificial intelligence navigates highly specific, difficult search spaces by utilizing learned priors and retrieved data, allowing polynomial time procedures to bypass brute force search. This creates an illusion of explicit knowledge. A trained system may display causal or theory-like competence even if it does not explicitly implement a formal mathematical calculus in its underlying code. Formal possession of a universal theory is entirely distinct from possessing bounded access to answers that simply accord with that theory. The system retrieves the correct patterns without needing to encode the first principles framework. Because of this, the practical bite of NP hardness remains. These structured gains do not uniformly apply to adversarial inputs or to novel puzzles that fall outside the system's learned regimes. AI performance is not the discovery of a universal solver. It is the weaponization of structure, priors, and verification games to make specific, previously intractable solutions efficiently reachable. Theoretical computer science must move beyond viewing complexity classes as static warning labels for intractability. Polynomial time contains deep internal structure. The polynomial hierarchy perfectly models how systems can exhibit progressively richer guided search behavior while remaining formally bounded. While this interpretation describes modern language models and agentic loops, its roots trace back to the foundational shift in the mid-20th century, the transition from studying pure computability to mapping bounded resource limits. We do not need to abandon classical complexity to understand modern artificial intelligence. The math has simply been waiting for the engineering to catch up. Complexity theory provides the definitive, rigorous formal language for understanding how structured access steadily widens the horizon of machine intelligence.